this lecture we will discuss about the smart grid protection schemes. As already we have discussed one particular protection scheme, that is the adaptive protection scheme for the microgrid environment, and we will continue from there. And already we have discussed that if we have like a radial network, this is our grid and there are different buses, and at different buses we have loads, and let us say here one overcurrent relay R1 and here one overcurrent relay R2. In the previous class we have discussed that this R1 is treated as the primary overcurrent relay to protect, to clear this particular fault F, and if this R1 fails, then this R2, which is treated as the backup relay, this R2 is going to clear this particular fault F, and the gap between these two relay operation basically 0.3 to 0.5 second. Now, this particular process of clearing this fault using this primary and backup relay within certain time gap, that is the CTI, coordination time interval, this particular time 0.3 to 0.5 second is known as CTI, is known as coordination approach of the overcurrent relay. And as I said from the beginning that in distribution network mostly we use in the 11 kV network the overcurrent relays, but due to the penetration of this renewable sources, let us say here one renewable source DER is present. Due to this penetration of DERs, what will happen? The current profile of different lines or the current profile seen by different overcurrent relays basically changed, and that particular current profile if it is changed, then the corresponding this block setting, that is if it is I and T, then this resultant current will change and corresponding block setting should be changed, and of course the corresponding TMS, that is time multiplier setting, should be changed. That means in general if you see that in our distribution network in conventional approach we use basically a fixed mode of like block setting and fixed TMS, but due to the integration of renewables or penetration of renewables, this fixed mode of operation of the overcurrent relay is not desirable. It has to be adaptive in nature, because every time this network is going to be changed with the presence of distributed energy resources or with the absence of this DERs, or due to the different modes of operation, like we have grid connected mode of operation, we have also islanded mode of operation, and also due to the presence of different types of renewable sources. That means if every time we are this particular relay will see different voltage or current profile. So, obviously this relay has to be the fixed mode of operation of the relay should be changed, and that is basically the way out towards the adaptive protection scheme for this smart grid environment. And this is a very preliminary discussion, a basic level of discussion that what is this adaptive protection scheme and which are very much essential for this smart grid operation. And you see that these are the step outs or ways out to have this conventional coordination approach of the directional, or it is a directional overcurrent relay. When this directional element is added with the overcurrent relay, then the together it is called as directional overcurrent relaying principle, which may be used for the smart grid operation. And here what we do initially, maximum positive sequence pre-fault current is basically stored or is calculated inside the process of the digital relay, and next by seeing this maximum fault current, corresponding TDS or TMS is set and the coordination time interval is set, and then corresponding backup fault current is of the relay, backup relay current is also set, and then the TDS of the backup relay. Basically there is a way out how to take the coordination from the primary to backup. Initially the primary relay will see maximum fault current. What is the maximum fault current? That should be calculated, and its corresponding TMS. Basically let me clear here one point, that in a string of operation like it is a radial network, and this is the upstream we are treating where the grid is present, this is the grid and this is my upstream side, this is upstream and this is my downstream. The power is let us say flowing from the grid side towards the load side or load centers. So, in that case basically what we do, what we treat, that the final the relay which is located at the end terminal or end feeder, that is R1, is having lowest TMS. The lowest TMS means the TMS, this particular TMS varies within 0 to 1, and this lowest TMS means it may be 0.1, it may be 0.2, it may be 0.3, it varies. And of course, this particular TMS setting is based on the lot of many numerous simulation studies of the network. See, when these relay settings are done, we have to simulate sufficiently the system or network before going to install the digital overcurrent relays or digital directional relays in the consigned or the prescribed network or the location where we are going to locate the overcurrent relay or directional relay. We have to test it, how this particular algorithm or idea or technique is going to be performed if it is so, and before going to implement in actual real field application. And that is why the testing is very, very important. And that is here the point I just mentioned. The lowest, I mean the towards the end of this feeder, like towards the downstream side, this relay we keep basically the lowest TMS. The lowest TMS means the time of operation relay should be very quick. If the very, I mean the magnitude of this TMS is higher, like maybe 0.8, 0.7, then the relay will take more time to trip for a particular fault position. And keeping all this, these are very basic concepts, maybe as far as the coordination of the directional overcurrent relay is concerned, and this particular coordination interval should be also maintained. And to be honest, here this DER, distributed energy resources, due to the penetration of the renewable sources, this particular decorum is not anymore constant, it may vary. As I said, because the current magnitude is going to be changed, the corresponding time of operation of the primary relay will change, the corresponding TMS also is going to be changed, and the corresponding time and the TMS of the backup relay is also going to be changed. That is why in general, in overall, if you will see, we need a very good adaptive protection scheme if the renewable sources are penetrated to the microgrid system. And for that we have proposed the first scheme, that is basically the adaptive protection scheme using the sequence currents. In this scheme what we did basically, this is the expression from the IDMT, characteristic based overcurrent relay, right. This is the time of operation, and this is our basically the PSM, the fault current to the clock setting into the TMS. TMS is the time multiplier setting. Now, if you could see this time of operation of the relay, this P stands for the primary relay, I stands for the location relay, and this J stands for the location. I stands for the which relay and J stands for what fault, right. At that location the fault has been incepted. Now, the C stands for basically the mode of operation of the microgrid system. Already as I have discussed, this mode of operation of the microgrid system is, to know this is very, very essential, whether the microgrid is connected to the main grid or it is isolated from the main grid, that is the islanded mode of operation. So, to know that, to incorporate that particular mode of operation, intentionally we have developed this technique, that this C, the TMS, this particular TMS is basically decided for this P means primary relay and for Jth fault location, and C is the mode of operation. What is the present mode of operation? According to that we have to also set the TMS. Otherwise, if the for a particular fixed mode of operation, fixed TMS we cannot use, because as the microgrid operation changes, then the TMS and clock setting should be changed accordingly. Then only it will be adaptive in nature. That is the first point. And second one is this IBCIJ, that is the time of operation for the backup relay. As I said that every primary relay has its backup relay, because if the primary fails to clear a fault, though it will be late in relay, but we have to clear the fault, and that job is basically done by the backup relay. And this TBCIJ stands for, B stands for backup relay, and the C stands for the mode of operation, and I is basically which relay, and J is the which fault position. These are some symbols, and the same expression we have written here. That means, if you could see these two equations, the time of operation of the overcurrent relay basically is dependent on this function f of mpj or f of mbj. That means, this particular function is dependent on this clock setting multiplier. that is this fault current. This clock setting multiplier is nothing, that is the fault current divided by the clock setting. This is the fault current and this is the clock setting. So, this ratio is basically the clock setting multiplier, we have already discussed in the previous class. Now, if it is so, that means my time of operation is going to be modulated or going to be changed if my fault current of the system, of the network, or the clock setting of the network is going to be changed. And yes, of course, if this TMS is going to be changed, then also my time of operation is also going to be changed. So, keeping all those exercise in mind or concept in mind, that how to set this time of operation for the backup and primary, so that we are not going to lose any healthy section. We have to just isolate only the faulty section, not the healthy sections. That is our target, so that we can just reduce the uninterrupted supply to the loads or the consumers. Now, we have just one concept here, that is this new TDS. What will be the new TDS? How it will be decided? This will be the ratio of this primary to backup function. This is a new one and this is a old one into this old TDS. Let us say, for example, I just want to discuss here what do you mean by this old and new concept. Let us this particular microgrid was operating initially in the grid connected mode. So, that will be my old particular operation of the microgrid. Now, let us say this, due to some fault on the grid side, this switch S1 is now open. Due to this microgrid is going to be operated in the islanded mode of operation. That means my new operation of the microgrid is islanded mode of operation and my old one was grid connected mode of operation. Now, I will just come to another point here, that after calculating this new TDS, what we will do? We will just calculate our corresponding time of operation of the primary and as well as the time of operation of the backup relay. And here one more point I will add. If you could see here that the time of this clock setting multiplier for the primary and the clock setting multiplier from the backup, these two. In case of clock setting for the primary relay, we have taken this I1Fij. This one stands for positive sequence fault current seen by the primary relay. However, in case of backup relay, we have taken this I2Fijc, that is taken as the negative sequence fault current relay. So, this negative sequence fault current relay is treated for the backup relay, and for the primary relay we have considered for the positive sequence fault current relay. The reason being is that if you could see that our aim is to how to coordinate the primary and backup properly without sacrificing their coordination. That is the main issue. Basically, what happens due to the integration of renewables, what happens before operating the primary for a particular desired fault position, the backup relay may react. That is known as miscoordination between the overcurrent relays. To avoid this, we have to set in such a manner the clock settings and corresponding TMS, so that the coordination between the primary and backup should be maintained. That is the main goal. That is what this coordination approach or the proper coordination functioning of the primary and overcurrent and backup overcurrent relays. Now, for that purpose, we have just derived or proposed this TDS, new TDS, which will be a function of course, the old TDS as well as the ratio of this F new to F old. If it is for the primary, the expression is like this, and the same expression holds good for the backup relays. That means, in overall, I just want to explain that using this changed TDS and changed this particular clock setting, we can always change the time of operation to a proper manner, so that the coordination between the backup and primary or primary and the backup will be maintained as it is. What is this miscoordination? It may happen that the backup relay will operate before the primary relay. That is one point. And second is that it may also happen that the backup relay will operate in too late. Let us say the CTI, the desired time of operation is 0.3 second to 0.5 second. Now, let us say this time of operation will exceed to 0.8, 0.9 or sometimes 1, and that time of operation is too late. That is why maybe in that way also the miscoordination will take place between the primary and back of overcurrent relay. So, those are the issues, and if you go through in different papers and research articles in nowadays in power delivery or maybe in IEEE different transactions and good journals, then there you will see that the research is just in a very booming stage, and they are trying to have very good adaptive techniques for distribution networks as far as renewables are concerned or microgrid system is concerned. Now, I will discuss another new aspect, that is we have added a new dimension we have added, that is a fault direction estimation using superimposed currents. As I discussed earlier, that this overcurrent element, then the directional element or directional relay. These two relays, their decisions are basically going to be ANDed to take the final decision, right. Here we are not going to use only the decision of the overcurrent relay to decide whether this is a faulty section or not, but we have to also add the decision of this directional relay, that is DR, directional unit, and this if both the relays like output will be 1 1, then the final output is going to be 1. So, this we have also proposed a new scheme for this directional unit. In general, basically many industries they are also following the angle between the polarizing voltage and the operating current. The angle can be deciding factor, like whether the fault is in front of the relay or it is behind the relay. Then only we can decide whether this we have to clear the healthy section or faulty section. That selectivity property is basically present with the directional relay. So, this is a system for what we are studying to propose this fault direction estimation technique using superimposed currents. The superimposed current means if you have a fault current, I mean this is a pre-fault current, this is our IT and this is a time direction, and let us say this is my fault current which has been increased. Let us say here is one fault is incepted at certain time t1, and this is a time axis, and this is my IT I1 and this is I1, this is I2, right. So, in that case what will happen, see here during fault, after fault, some fault current component, some current component is basically superimposed with my pre-current. That means this particular superimposed current component is known as superimposed current. We denote like this, delta I is equal to I fault minus I pre. These are in basically in phasor mode, right. This delta I is equal to IF minus I pre. Now, this superimposed current delta I is equal to the differentiation of I fault, the phasor, minus I pre phasor. These two phasors are subtracted from each other. If I will subtract this I pre from my I fault, then whatever the component I will get, that will be the superimposed component. And this is the corresponding circuit to analyze this relaying platform, and this is the corresponding positive sequence equivalent network for this particular single line diagram of the microgrid system, where we have one unbalanced load, we have grid and we have DER. Now, you see that we have taken this mesh network, this is my mesh 1 or loop 1 you can say, and this is my loop, we can design it loop 2, and this is loop 1. By considering these two loops, we have to solve to get the I pre current and I fault current, because we have to calculate the superimposed component of the current. And where we have to calculate? We have to calculate at this relay location here, and if you could see, the relay is located at bus G. This is basically the directional relay location, and at that relay location we are going to calculate this delta I, that is IF minus I pre. So, our target will be to calculate this IF and I pre. These are the equations for the loop 1 and loop 2, and by solving this we will get our I1 pre is nothing, that is I1E minus I1H. This is very simple. If you solve these two simultaneous equations, we have two unknowns, two currents, two unknowns. So, two equations we can solve, then finally getting this I1E and I1H. The output of by solving this equation we will get I1E and I1H, and if we take the difference of these two currents, then we will reach at I1 pre. Why this is I1 pre? Because if you see, this is my basically the I1 pre. So, here the current which is flowing is basically the difference of this two currents. Now, what is this I1E? The current contributed by this source VE, and this I1H is nothing, the current contributed the source VH. See this particular picture, the current which is for this particular relay, the location is here, this source VE will contribute some current, let us say that is I1E, and this VH will also contribute one current, that is I1H. So, if we take the difference, assuming that this we are just taking the convention left to right as plus and right to left as minus. So, by taking this difference, so I will get I1 pre is equal to I1E minus I1H, that is what the first expression of I1 pre. Now, we are in the process of deriving the fault current at the relay location. From the beginning I said that this directional unit is based on the superimposed component of the fault current or the current component. So, to calculate this superimposed current, we need the I pre and also we need the I fault. So, for the first part we have calculated this I1 pre expression, and the second part we are going to calculate the fault current position, and finally we will draw the phasor diagrams where this I1 pre will lie, where this I1 fault will lie or I2 fault will lie. So, accordingly we will just calculate the angles. Now, this is a calculation for the fault position F1, what will be the fault current seen by this relay, and that fault current is denoted by IF1 and that fault position F1. And similarly, if there is a fault at F1, now the corresponding circuit becomes like this. This is the corresponding positive sequence network. Now, here we have 3 loops 1, 2, 3 and 3 currents IE, IG and IH. By solving these 3, we will get the corresponding fault component, that is I1 F1, the positive sequence fault current component. It is very easy, that you could see here previously, as I have discussed for my case of like pre currents. Here you can see this V and VH, the corresponding currents, and this is the resultant of this I1 F1. These two current resultant will just derive the fault current which is going to be seen by the relay which is located at bus G, and this is the fault current for my particular fault position F1. Now, for fault F2, this is the corresponding expression or the equivalent circuit for the network. Now, after solving these two equations, so these are the equations like expressions for I1 F2. It is very easy, just simple mathematics we have to calculate, and the corresponding fault current expression we have to find out. And remember, in this case we are just searching for the position, phasor position of IF1, IF2 and I1 pre, so that we can calculate the corresponding difference between this fault current and pre-fault current, which is basically the superimposed current component. And let us see, here already we have discussed this superimposed component of the current is nothing, this delta I1F is nothing, the fault current phasor minus the pre-fault current phasor. Now, you see that finally we have reached here. See, this is V and VH, and this is my I1 pre. As I said, the current contributed by this V and VH, the resultant is basically this I1 pre. And in general, in a power network, our current, this network is basically inductive in nature, and in case of distribution network, the angle is very low, and this angle, this I1 pre is lagging almost by very less, 2-3 degree with respect to the voltage which is available at bus E. And if you could see from the previous mathematical expressions, this is the position of I1 F1 and this is the position of fault current position for fault position F2. By knowing this fault phasors, let us say we are now going to calculate the superimposed component for fault F1. What will be the superimposed current phasor position? If this is the fault current position for F1 and this is the I1 pre position, so that means our delta I1 F1 will be like this. So, it will just join from with respect to my I1 pre if I will add this component, it will reach to my fault component. Now, the corresponding parallel component phasor value will lie here. So, this is my superimposed fault current for the fault position at F1. That is basically the fault which is present behind the relay, right, just back side of the relay. Now, in the similar manner, the fault current, this I1 F2 lies here. From the equations you can just derive the position of this I1 F2, and now the corresponding, if you will add the corresponding superimposed component for this fault position, then it will, the corresponding parallel phasor will lie here. That means we got the two, the superimposed currents for fault F1 and F2 positions. And now let us see what will be the angle between the superimposed fault current and the pre-fault current. Here let me clear you that in this case, this I1 pre is taken as the operating quantity. Now, this delta I1 basically F, it may be F1 fault or it may be superimposed F2 fault, and this is treated as, let me correct it, this I1 pre is known as basically the polarizing quantity PQ, and this delta I1 F is taken as the operating quantity, right. Now, as I already discussed, sometimes in some researchers, some techniques they use voltage as the polarizing quantity. Here we have taken current as the polarizing quantity. Now, in this case the directional element is not dependent on the voltage information, it is only dependent on the current information. Now, this I1 pre is basically this polarizing quantity, and this superimposed fault current component is treated as the operating quantity. Now, let us see what will be the angle. This I1 pre and delta I1 F, this delta I1 F is leading to I1 F, because in phasor we always consider in the anti-clockwise direction, not in the clockwise direction, we consider in the anti-clockwise direction. So, that is why this delta I1 F is leading with respect to the I1 pre, and the angle between these two, if we will tell this phi 1, basically I have written here this phi F1 is angle between this delta I1 F minus I1 pre. Now, this angle will be positive, because the angle of delta I1 F is higher, greater than this I1 pre. Now, similarly, if you could see here, this delta I1 F is lagging to this I1 pre, and this angle will be negative and this will be positive. And this is the rule base basically how to decide that in what direction the fault has been incepted. If it is positive, then this relay will declare that the fault is just behind this relay, this is my F1 and this is my F2. So, that means this directional relay will say if this angle is positive, then the fault is behind this relay, and if this angle is negative, then this relay will say that the fault is in front of the relay. Now, these are the rules as I said. Now, the question is, if the in this case we have to keep in knowledge the power flow direction, whether the power flow is in upstream or downstream side. If it is from upstream to downstream side, then the first rule plus minus. If it is in the downstream side, then the rule will be just changed, minus and plus, because in that case if the fault direction, this pre-fault current direction changes, that means the I pre position is going to be changed in the phasor diagram. Here you can see, if this is my I1 pre direction when the power flow is basically from left to right, this is my relay location, then this will be my I1 pre. Now, if this current direction, power flow direction changes, then the corresponding current direction will be changed, it will be I minus I1 pre. That is why this instead of I1 pre here, so it will be just opposite to this, this will be I1 pre dash, and that is why the corresponding angle will be opposite. Now, this is a total flow diagram, how this particular technique is implemented. First one is sample the voltage current at 1 kilohertz sampling period, as we are not using here voltage information, only the current. So, we have to sample the current signals at a sampling frequency of 1 kilohertz. Second, we have to detect whether there is a fault or not. If there is no fault, no need to trigger the directional unit algorithm, and if there is some fault, and that particular fault will be detected using one cycle to cycle based fault detection technique, then only this processor will calculate the phases of the current using this DFT, that is discrete Fourier technique. After that, we have to calculate this positive negative sequence components, and because negative sequence component will be needed for the backup relay fault calculation. And this particular this particular section is for the overcurrent relay, and this particular section is responsible for directional relay. And here we are going to calculate the fault current and also this clock setting, TMS, and corresponding time of operation using our previous proposed methods already we have discussed. Now, this unit will be responsible for finding this angle between this delta IF and I pre. Yes, of course, it is positive sequence based superimposed current, fault current, and positive sequence based pre-fault current. If these two, the time of operation is okay and this angle is okay, if it is within the limit, within the desired set value, then the decision is going to be taken. And this particular system we have tested, this particular technique we have tested using a simple technique, simple network like 4 bus network here, and these are the relays you can see for this line EG. This is the one relay protecting, and this is R2, and here we have this line R3, R4, and here for F3 we have R5, R6. For F2, let us say for F2, this R3 is treated as the primary relay, and which is the backup relay? The backup relay is R1. Similarly, for F3, R5 is the primary relay and R1 is the backup relay. So many combination will have, like for F1, R2 is the primary and R4 is the backup. So, we have different pairs of overcurrent, directional overcurrent relays which are going to be coordinated using the proposed technique. This is a sample result. You can see here this particular technique operates fine, and this is the adaptive approach what we have proposed, and this is a conventional technique. And here the main point, the CTI, I just want to mention that for fault F1 position, this R1 is basically the primary and R2 is primary, R4 is the basically backup, R6 is also backup. In that case, the time of operation CTI is within 0.301 second. That means that time of operation, that coordination is perfect. And here also, if you will see, the technique exceeds like 0.306, 0.35, 0.37, it exceeds 0.30. Here our CTI, desirable CTI is 0.3 second. It should not exceed 0.3 second, which is actually obtained by this adaptive approach. This is for another result, islanded mode of operation, that the proposed approach operates properly and the conventional approach fails. And this is the result for directional unit. You can see here for different faults, different mode of operations, M1 grid connected mode, M2 islanded mode, M3 disconnection of DRs. So, for different modes, for different faults, this AG means phase A to ground fault, this is 3-phase fault. The corresponding directional unit operates perfectly. Thank you so much. Today we have this much.